So next we have Karl Hibbitts, and he'll be presenting on simple camera concept for surface volatile characterization and mapping.
Hey, good afternoon, everybody. Go ahead and move to the next slide. I'll be talking very simple camera concept using high TRL components for a camera that operates from a moving, unstable platform. So we're kind of leaping into the future here to when we have humans on the surface wanting to exploit, prospect for resources of water ice. So this is a nice follow-on to Paul Haynes' discussion about looking for thermal cold spots. We are looking for water spots, or we're looking for carbon dioxide spots, or any particular volatile that you're interested in. The argument that we're going with today is that if you pick a single material that you're interested in, a simple RGB approach, not the visible wavelengths, but infrared wavelengths, can answer the question for you. So we're going from, on the left, a panchromatic capability with a Hasselblad camera, to the one on the right, where an astronaut or a rover can carry with them a camera that detects water. Next slide, please. The traditional approaches for detecting water are push broom technology, or for the Viper rover, a AOTF approach. It's hyperspectral. And these work very well when the motion is well known, such as push broom, or when the rover is stopped and static and you have time to run through multiple filters. However, in the next slide that we get to, we will see that this will not always be the case. These are some extreme examples of what astronauts may do on the surface of the moon. And additionally, rovers may also not want to pause when taking measurements. So our premise that we need a camera that works, that is able to instantaneously provide information, imaging information on the distribution of what volatile you're interested in. We're anomaly exploring water ice as our case study. And we have some internal work at APL exploring this. Next slide, please. We do this spectrally with as few as 3 bands. 3 wavelengths are needed in order to characterize the discrete absorption features associated with the material of interest. In this case, again, we're looking at water ice on the left. We're looking at either bulk water or azure water on the right. 3 wavelengths are needed in order to characterize a band, whereas 2 will be affected by photometry. Keep in mind that the illumination conditions are not constrained on when observing from a rover, from an astronaut, unlike from orbit. Next slide. And on the left, the reason the wavelengths there were a little bit shorter than one might consider optimum is that for an astronaut carried or a rover carried inexpensive instrument, one may want to limit themselves to uncooled sensor technology, such as the in-gas, which stops at 1.7 microns. This shows that will work. On the right, one has to keep in mind one has to use cryogenic technology, though, so that is becoming less onerous for cooling as time moves on. Next slide, please. This is not a new idea. Using few bands to detect specific materials.
2 minutes, Bo.
Yeah, thank you.
Right.
As demonstrated by the flashlight mission, was using active multispectral spectroscopy, not quite imaging. On the right, we developed a camera using actually multiple cameras that incorporate software to instantaneously, at video rate, combine the images at 2 wavelengths. Technology is now available to do this for 3 wavelengths. So in this case, we were detecting plastic objects in the natural environment. We can also tailor this to detect water ice in the natural lunar environment as well. So next slide. The 3 technologies that are really high TRL, and this kind of camera can be built relatively quickly, are the Bayer pattern camera. Dave Blewett is leading effort to develop this for geology in the V-near wavelengths. And we are exploring the possibility of doing this at the infrared wavelengths using in-gas detector, as I just talked about. The advantage to this is that it's a single camera, uncooled. However, it sacrifices some spatial resolution. And with IR arrays, we may want to preserve as much spatial resolution as we can. The next 2 approaches attempt to do that. The middle one is actually a prism camera that's available off the shelf using prism technology. It preserves spatial resolution with 3 detectors. It reflects the light into each of them. Of course, it takes 3 times the power. And on the right, we have a multi-camera approach. This takes 3 times as much power, but it's software driven. Next slide, please. We're almost done. And next slide. There we go. And this is just demonstration that the wavelength or the filter technology that is COTS on the left can be modified and would meet the requirements as shown on the right. And then skip to the next two slides and we'll end with conclusions. Next one, leave that up.